Well, I'd like to welcome everybody for attending today on a gemstone that we don't hear as much about as we used to, Zircon. And we're going to have an interesting star-studded cast of speakers and presenters, with the exception, of course, of myself. The order of service, if you will, is I'm going to do initial introduction and a little review of the gemology of zircons. Then we're going to move on and see some amazing shots of the some of the zircons that are in the collection at the British Museum of Natural History in London, England, by its curator. And then we'll move on to learn some very interesting information about zircon as it's being used to tell the age of things in the world, by Dr. George Garrels. And then finally, we'll finish off with one of the world's top facetors, Daniel Hugh, I hope I'm saying that right, who will share with us, I'm hoping, a very interesting review and overview of his trip to Cambodia, one of the most fabulous locations worldwide right now for high quality zircons. So with that in the offing, I'm going to start things with my brief presentation about the gemology of zircons. That would be helpful if it worked. Oh, come on. Help anybody. Oh, there we are. And just so you know, there is some confusing aspects to the names that have been given to zircons over the years. And starting off, we had hyacinth and jacinth, and those were really used in ancient times to refer to reddish brown zircons. And later on, we had, I think, probably an Indian term, jargoon, for yellow zircons. And in the present day jargon, if you will, zargun, the Persian word, was for gold colored, was bastardized and turned into zircon. And this has happened an awful lot with gem names over the years. Like, for example, turquoise was really the English anglicization of Pierre Turquoise. And so it told us about its origin. In this case, it told us about its color, or the color of the commonly known examples of zircon. Now I'm having some issues with the way the slides are coming here on my screen. I'm losing my part of my screen to people's faces. I don't know how to make it smaller. But the reasons to love zircon as a gem, number one is color. And there are only a few gems in the gem kingdom that have as wide a range of colors as zircon, and they would be the beryls and the corundums and the spinels. I would say that's about it. And so this is actually a blessing in disguise for those who may love zircons, because this is a stone that can be very colorful. Now, the color range in zircons is red. It can be quite a vivid red, blue, and it can be very intense blue, yellow, ranging from pale yellow to yellowish brown to reddish brown, colorless orange, and a vibrant leaf green, with red, blue, leaf green, and colorless as the most valued colors. And I would say that the colorless, being a highly valued variety of zircon, has faded away, and we'll talk about that in a minute. And of course, one of the big things about zircon is that it has a really high refractive index, which I believe is higher than diamond. Someone can correct me if I'm wrong on that, at 1.992. And that allows it, when cut properly, to be very refractive and very attractive. And for this reason, for at least a century or more, colorless zircon was nicknamed the poor man's diamond, since it was harder than quartz and therefore didn't scratch easily with the dust in the air like other stones. But it managed, when cut properly, to refract light in a glorious manner. And more recently, when we've, over the last 4 decades at least, we've had many very useful and interesting diamond simulants that went from barely imitating diamonds to being hard to determine from diamonds, and with simulants such as cubic zirconia, which were immediately much more cheaper and readily available because they were synthetic, and they rendered colorless zircons as too expensive and definitely not as desirable as the other diamond substitutes. So price and availability certainly made a difference in this end of the zircon color range to be still valuable and highly prized. And finally, reasons to love zircon as a gem: lower grades of natural zircon can be vastly improved by simple treatments, which usually involve heat. And I'm going to be oversimplifying this to be sure. So the geologist coming up ahead of me, George, I hope you'll make this even clearer, talking about the geology of the zircon. But as a gem mineral, it was first formed in igneous or hot melts and solutions, and basically started off life in the rock itself or in pegmatite formations. However, most of the zircons worldwide are not found in the hard rock locations. And as we know, it's harder to get good quality material out of hard rock than it is out of alluvium, because the alluvial deposits have already pre-banged, pre-broken, pre-chipped, we hope, and knocked away all the weak areas of stones. And therefore, what you get in most alluvial deposits is a much cleaner stone than you'd get out of the rock where it was originally formed. And what happens is the processes of erosion have worn the crystals, which are hardened to 7.5 in their best forms, out of the mother rock and deposited them in streams or riverbeds, either old ones that are now buried or current ones that are still active. And because it's perhaps the heaviest natural gem, it is relatively easy to separate out from other materials and gems when panning in these locations. And a lot of them are actually under heavy clays and are usually at the bottommost parts. And the interesting thing of looking for gem zircon is, since it is so heavy, it usually is found in alluvium that's closer to its original deposits than even diamonds would be because of the heaviness. And therefore, it takes a very strong current to move it farther away from its point of origin, geologically speaking. Zircons are found in a great number of places around the world, not as widely found as some other gems, but in the olden times, most of the world's then known zircons came from Sri Lanka. And I have seen notes of a small deposit in France that had quite beautifully colored red zircons, but it wasn't really a commercially viable size deposit. And I'm not certain if it's still being mined, but I do believe that people are still finding zircons, red zircons, in that location in France. But in more recent times, we're seeing some fairly decent zircons coming out of the mud tank in Australia, although most of them have been brownish in color and are subject to and capable of being improved through treatment, and they can be quite large. Well, this is, by the way, not one of the larger crystal gems out there, so large zircons are not that common. Russia, Thailand, Brazil also produce small quantities of cuttable stones, but new areas like Cambodia are now producing some of the best qualities of zircon in the world, and also in quantities that are viable as well. Also, a lot of locations, and I say quite a lot compared to other places, have been found in Tanzania. Brownish red ones to red have been found from Mashua and Kwagwe, and in fact, up to 3-inch crystals for this mineral. That's actually a good size. And pale yellow stones have been found from the North Pauri Mountains, Panda Hill carbonatites, and in the Singida areas. Tanzanian browns and yellow stones will yield beautiful blue stones after treating, so they're very viable and useful as gems. Now, this is something that I was in complete ignorance of, and I shouldn't have been, but upon doing a bit of research, it's clear there are 3 types of zircon according to the way they've been formed and the stages of stability or instability that are present. The high zircons have the highest refractive index, up to 1.992, and therefore the highest dispersion, and they have the highest specific gravity. And they represent probably the heaviest in terms of density of all the gems that are in the gem world. And they have their highest hardness of known zircons, which is 7.5. And this is notable because the hardness deteriorates to a lower level as you get into the lower levels of zircons. And the colors most often found in high zircons are blue, light green, yellow, and colorless. And there's been demonstrated some weak double refraction in the high zircons, but mostly found in the blues. And of course, the luster of the high zircons is adamantine, which of course was one thing that would put also in its favor as a diamond simulant. Intermediate zircons have the problem of having been partly decayed by radiation. And this is because zircons are sort of a unique stone that incorporate within their lattice structure radioactive elements, which by the very nature of them being radioactive over time cause deterioration, not only of the lattice structure, but also of the overall structure of the crystal, and causing it to be less distinct, and also changing some of the properties because the colors are not as distinct. Some of the green, brown, and yellow stones are commonly found in intermediate zircons. And sometimes when you're looking at a cut stone under the scope, you can see faint parallel lines, which one author noted were looked like a partially opened Venetian blind. It may be improved in all aspects to becoming the equal to high zircons by appropriate heating technique. And this is rather interesting because the heating actually changes the structure and moves it up the scale of zircons into high from intermediate. So you can make a intermediate stone basically into a high zircon by using appropriate heating techniques. And low or metameric zircons can be a brilliant leaf green, which is one of the desirable colors, but that would be the high end of low, and deteriorating into greenish brown and brown. And low zircons have the lowest refractive index and the lowest specific gravity, which is below 4.6. And they may be so degraded by the attack of radiation from within that they may be reduced from crystalline to amorphous. And the high end of low can be improved by heat treatments, but one of the notable immediately visible aspects of the low is that its luster is no longer adamantine. It's now more greasy in nature. And so this is something that makes it easily distinguishable from intermediate and high. Now, the treatments most commonly used on zircons, and I would love to stand to be corrected on this when I'm done, are usually involving heat. The technology and the information that I'm talking about through most of this presentation are somewhat dated, and I'm sure there are those amongst you who are very much more well-versed in the more modern technologies that are being used now for ID and for evaluations. So just bear in mind that what I'm talking about may be not 21st or 22nd century information. But heat is definitely an important aspect in the treatment of zircons. Since most of the world zircons are not of ideal color, and there are more intermediate than high types of zircon, the rough is sent to places like Thailand for special heat treatment. And brown and yellowish brown stones from places like Tanzania and Australia are put in a heated vacuum, basically devoid of oxygen for 10 or more minutes, and then allowed to cool slowly. And part of this is to allow stresses to be relieved because heating does energize and change the structure of the stone. And so it takes time for it in cooling down. It must be given time to reestablish its structure without failing and cracking and showing damage. If yellow or colored stone, this process, by the way, does yield in many cases a very nice and desirable blue color, which is one of the more valued and prized colors in zircons. But if a yellow or colorless stone is wanted, then not only are the stone heated.
Water? Here, water.
Someone needs to be muted here.
You want some water to drink?
Please mute. So if you want a yellow or colorless stone, then is desired, then not only they're heated, but they're heated while exposed to a stream of oxygen. So basically, it's an oxidizing process, and the end result is a nice yellow stone or a colorless stone. But again, the world is not seeking colorless zircons as much as it used to, thanks to the onslaught of good simulants of diamond, much better and much less expensive than zircon. So the heating of low and intermediate zircons can cause a form of internal restructuring and redefinition of the crystal lattice into that of a higher stone and or perhaps even a high stone, increasing the density and the specific gravity, as well as changing a low stone's greasy luster to the adamantine luster of a higher stone. And I think this may be unique amongst gems, made possible by the fact that zircons have perhaps the widest naturally occurring range of specific gravity of any known gem, at least as far as I was able to discover. Now, I'm sorry, I think pretty sure the picture here is of a diamond cutter, but it's hard to get pictures of cutters. So my apologies to Mr. Daniel there, because if I had a better picture, I would have definitely shown it. But one of the things that's helpful when you're doing evaluations of stones is to know what the ideals should be. And from what I was able to ascertain, the ideal cut was designed in some circles as a way of trying to overcome the double refraction that can be a problem in stones like zircon. And part of it was done by modifying the brilliant cut, which is one of the more common cuts used for zircons. And they put an extra row of facets around the pavilion to add in the terms of the brilliance of the stone. And using a 40-degree angle for both the pavilion and the crown seemed to have also helped bring more life and less fuzziness, if you will, to the zircon when viewed from above. And this was, I think, called a zircon cut, and I gladly will be corrected if I have this information wrong. A couple of quick, simple tests, not always definitive, but maybe as additional to information you may already have. Zircon may be the only gem in the world of gems to, we looked on through the spectroscope to show distinct lines for uranium, erbium, and sometimes thorium. So this is something that might be definitive, and someone again can correct me on this. I'd be glad to hear that. Under long wave ultraviolet, zircons may glow in a weak yellow to orange color. But shortwave ultraviolet, which of course usually has far more range and brilliance when viewing stones that may fluoresce, will cause mostly the blue stones or colored zircons to have a relatively strong yellow or orange glow. And some blues, to add as an extra determinant, will have an afterglow, a white afterglow, which is called phosphorescence, after exposure to a strong shortwave light. So these are simple things that you can add on to the tests you already may have. Now, using a Chelsea filter, greenish zircons will show a reddish hue, and I'm suspecting that might be through, for some reason, have something to do with the presence of chromium. But the coloring agents in zircon, generally speaking, I've been told, are related to their radioactive elements of uranium and thorium. So I'm not quite sure why it has a reddish hue. Someone can explain that to me later. And blue zircons will tend to show a greenish hue when viewed through the Chelsea filter. So these are just a couple of simple tests. One of the problems with treating stones is that sometimes the treatments are not as permanent as we would like them to be. And this is definitely the case in the world of zircons. And that is, over time, it has been noted that blue treated zircons may prove to be somewhat unstable after they've been exposed for a prolonged period of time to the sun and the ultraviolet spectrum of light. I have no data, and I would love to hear this, to show that this also happens to naturally blue zircons. So if anybody has some information to corroborate that this is something just for treatment, or that it actually exhibits itself as well in natural blue zircons, it would be interesting to know. And there is some dichroism present in zircons, but it's mostly evident in the blue form, although it's present in other colors, but it's very substantially weaker and maybe unnoticeable, except to the very trained eye. I would love to know, though, if this is the source of color change in blue zircons from Cambodia, or if this is another process that's involved. So I throw that out there for those who are knowledgeable in the audience. So just a quick nod to the very simple sources I used to put together this presentation. Gemstones of Africa, Precious Stones, Introduction to the World's Gemstones, Gem Identification Made Easy. Thank you, Antoinette. I didn't know I had one of your books. Encyclopedia of Minerals and Gemstones, the Gemologist Compendium, Color Treasury of Gemstones, and Planet Earth Gemstones. I have a fairly extensive gem library, and I just pulled a few books to try and put together this talk. So I would then like to stop sharing and open the floor for any questions or contributions at this point. There's so many talented, knowledgeable people out here. Please help me here. All right, well, then if that's the case, then we'll move forward. The next person on the roster is someone who I have a great respect for and who's been actually a presenter in the past. And we are always grateful and thrilled to see what she has to show us from her personal collection at the museum. I would so love to be a curator. What a lovely position to be in charge of all the things that you are, Robin. So without any further ado, I'd really like you to welcome Robin Hansen from the British Museum of Natural History, London, to share with us pictures of what she has in her collection of fine zircons to be shown and enjoyed.
Thank you very much, Ray. That was really nice to listen to the talk about zircons, and hopefully you guys will enjoy looking at some images. Let me just share my screen. Okay, can everyone see that? Sorry, I'll just rearrange my screen.
We can see it.
Good. Okay. Oh, hang on. Okay, so yeah, thank you very much. So my name's Robin Hansen. I'm a curator of minerals and gemstones at the Natural History Museum. So I do have the pleasure of working with quite an incredible collection, and it was fun to have a look at some of the zircons. So first of all, I thought we're just showing some of the natural color range of zircons. So you can see lots of lovely autumnal colors, lots of reds, yellows, browns, oranges through to sort of greens, and then also some purples and blues. So natural blues, reds and colorless zircons are actually quite rare. And so as Ray was saying, it's much more common to get these yellows and green colors. And you can also see in the image that most of the zircons have been cut with either a rounded oval or cushion cut or an octagonal shape. This is because zircons are quite brittle, so they cut them with these rounded shapes with no corners in order to give them a bit more protection. So this is a slide showing some of the different colours by the heat treatment. So you can see you've got those lovely sky blues, but also the colourless zircons, and then really nice golden brown one in the middle there. So I thought we'd take a quick look at some zircons that we've got from specific collections within the gem collection. So the first one is Sir Arthur Herbert Church. And in fact, Ray, I noticed that one of your references that you had was for A.H. Church, who I assume is probably the same person here. So Church was a famous British chemist and artist. He had a lot of expertise in both mineralogical and paint chemistry. And following his death in 1915, his wife presented 170 gemstones set into 162 gold rings, plus another 33 unmounted faceted gemstones. And the whole collection is very rich in spinels, garnets, tourmalines, and also zircons. So Church did a lot of research, including the characterization of minerals and gemstones, and he discovered several new species, and churchite is named in his honor. So you can see here, these are some of the gems that we have on display in the museum. So I just wanted to show you sort of the different colors that you get. The beautiful blue one in the middle at the bottom there is from Sri Lanka, and it's just over 9 millimeters wide. And the colorless one, which is just to the left of that, is from New South Wales in Australia, and that's on 9 millimeters wide. So Church is actually credited as the first person to use absorption spectra to identify gemstones, and he published in 1866 this discovery by spectroscope of absorption bands in both zircons and also almandine garnets. So unsurprisingly, of the collection, there's actually 63 zircons that we have from Church's collection. So here's a couple more. That lovely emerald green one in the middle there is 11.5 millimeters wide. And I thought just the color of that orange one in the bottom there is really quite stunning. You'd almost think it was a fire opal if you didn't know you were looking at a zircon. So another collection we have is of Arthur Payne. He was a gemologist, a gem dealer. He lived in Mogok in Myanmar and co-owned several of the mines. So he created quite a representative suite of gems, including zircons. So these are some of the zircons that we have on display in the museum. They're all from Mogok. And the other thing about Church was that the mineral painite was named in his honor, which is one of the rarest gem minerals. So this one, the octagonal yellow zircon, you can see is nearly 36 carats, and the red circular one's just over 20 carats. So this gemstone at the bottom here, this is the biggest faceted zircon that we have in the collection, and it's 100.63 carats. And it was acquired in 1926 from a gem dealer in Hatton Garden in London. And yeah, quite stunning when you see it in person. We also have this lovely intaglio. Now, this was engraved by a gentleman called Wilhelm Schmidt. He grew up in Ida Oberstein and was an apprentice in Paris, learning all about the art of gem carving and engraving before he moved to London with his brother, Louis, and they set up a shop in Hatton Garden. His brother was a gem dealer, and then Wilhelm worked as a gem engraver. So really nice combination. And we have quite a few gems that have come from them in the collection. And he was well known as a gem carver for working with these more difficult materials, such as labradorite, opal, and also the zircon. So it's quite an accomplishment, again, knowing that zircon can have that brittleness to it to be able to do such a fine engraving. So this one was acquired in 1893. So a heated gemstone that we have on display, it's this lovely blue one. It's a rectangular step cut. It's listed as coming from India, but I suspect it's probably more likely to be Sri Lanka, and then it was cut in India and came to us from there. Hence, when it was registered, we have it listed as from India. And hopefully on your screens, you can just see some of that double refraction by seeing the doubling of the back facet edges. So this was presented to the Natural History Museum by a gentleman, Charles Matthews. He, again, was a well-known gem cutter based in Hatton Garden, and his son also was part of the business. Oh, beg your pardon, I have said it's a step cut, and it's not. You're absolutely correct. So he was a well-known gem cutter, and his son also worked in the business. And in fact, we also have the pleasure of having the Matthews gem collection in the museum as well. This lovely one I put because I really like the colour. I suspect this is probably an intermediate garnet. You've got a slight mistiness to it, sort of a bluish green. And then I think there's probably a scattering of the light, which gives the effect that you're getting sort of yellowish. When I took the photo here, the sun's coming in from a window on the right. And so you're seeing that lovely yellow colour on the left of the gemstone there. So this is one of 4 zircons that was presented by gentleman Mr. Brukowski in 1884. This one definitely is a step cut. It's a lovely red stone from Australia. It was purchased from a gentleman Forster in 1870, and it's 9.32 colours, but very clear gemstone. I'm not sure exactly where in Australia it comes from. I'd have to have a look. It'd be interesting to see in 1870 which particular deposits they were mining to see whether or not we can link it back to a more exact source. And this one, a nice sort of pale cinnamon brown colour, just over 5 carats, 5.21. It was purchased in 1889 from James Reynold Gregory. He's a well-known British mineralogist and dealer who sort of worked in the mid to late 1800s. And this was actually one of a selection of faceted gemstones that were purchased from his own private collection of gemstones. And I put these ones in for Ray. They're two really lovely twin crystals coming from Eganville in Ontario. So a couple of slides just to look at the properties. So as Ray had said, the hardness is 7.5 on the Mohs scale, but because zircons are quite brittle, this can be another way you can sometimes identify them, that you get these relatively scratch-free facet faces, but you get this nibbled look along the facet edges due to the brittleness where all the little edges are broken off. Also, the strong double refraction, you can see in these two images, we've taken photos through the crown facets. So you're looking more through the side rather than the table of the gemstone, and you can quite easily see that doubling of the back facets. So as Ray was saying, the cutters would then orientate the rough in order to not have this effect very strong when you're looking through the table. Otherwise, you do get quite a blurry looking stone. And then lastly, just to sort of show a comparison, looking at that specific gravity, because zircons are much heavier, these two gemstones, zircon and tourmaline, they're actually the same carat weight, but you can see that the zircon is a much smaller gemstone because it's got that much higher specific gravity. So that's it. So I'm happy for any questions. I'll stop sharing as well. There we go.
Thank you very much, Robin. That was exciting to see some of those stones, especially well presented and lots of background information. I thank you very much for taking the time to put that together for us. It's always a joy. Now, our next presenter is a gentleman I'm very keen to hear from, Dr. George Garrels. George has got his Bachelor of Science out of the University of Arizona and his Master's of Science out of the University of Southern California and his PhD at Caltech. And he's been a professor of geosciences at the University of Arizona since 1985. That means he might be as old as I am. His research has focused on the uranium to lead geochronology and how it's used to study the Earth's history. And from what I've seen and heard, this is leading edge stuff that is very, very important, and such that his lab has a grant from the science, oh dear, can't remember what it's called now, but the government body that funds research, and so it's interesting to know that for what he does, zircon has proved to be his primary mineral used to determine geochronology. So zircon is basically a geochrome. And I'm looking forward to hear now more about this, because this is, for me, a relatively new area. I've noticed from gemological articles, there have only been a few recently done in the last 5 years or so that address the subject of geochronology. So I would suggest that what's going on that may be headed up by what's going on in George's own lab. And although he's probably too modest to say that. So I'd like you to welcome George, and I'm looking forward to learning a lot more about zircons and geochronology.
Well, thank you very much. I'm very pleased to be here. I have learned a lot this morning already. I look at zircons, but I see them in a very different way, and that'll become apparent as we go through my slides. I'm going to share my screen. And I've probably got about 45 minutes worth of slides, which is kind of a long set, but I'd like to stop along the way. If anybody has a question, they'd like to stop me intermediate, that's fine. Let's just jump into the chat, and maybe Ray, you can help me monitor that. Let's have a look at some slides first. And so my presentation today is going to be mostly focusing on the use of zircon as a geochronometer. And my background in geochronology comes from my operation of the Arizona Laserchron Center that will be featured a few times during the slide presentation today. And our research is funded by the National Science Foundation.
That's it.
Everything okay?
Yep, that's the one I couldn't remember.
Yeah.
National Science.
Yeah, good. And so let's jump in. I just made up this word. This is the Zircron Revolution. And I use this term because it's kind of a revolution in terms of other chronometers. On the lower left here is sort of the history of geochronology from the 70s, 80s, 90s, 2000s. And the red curve here is what has been going on with uranium lead dating of zircon in the last 15, 20 years. And this is the kind of continuation of that curve. This is the number of papers that are published per year that contain uranium lead geochronologic information using the mineral zircon. So this is just exploding. There's so many different uses of zircon as a chronometer, and that's really what I'm going to focus on today. So I'll title this Why Zircon is King. Zircon is king as a chronometer for several different reasons. Of course, it's zirconium silicate, and so zircon is common in many rocks within the crust. Ray mentioned this, most igneous rocks, if they have quartz, they'll contain zircon. So most igneous rocks on planet Earth in the crust anyway will contain zircon. Metamorphic rocks will grow zircon during metamorphism, so we can date the age of that metamorphic history. And then as Ray mentioned also, many zircons are found in sedimentary rocks. If that sedimentary rock, like a sandstone, contains quartz, it will contain zircon also. So as a chronometer, zircon is great because it has high uranium concentration, 100 to 1000 ppm, has moderate thorium concentration, but it has low lead. Since we're going to be using the uranium to lead decay system, it's great to have a lot of parent and not very much daughter. It also contains lots of interesting trace and rare earth elements, and we'll talk about how to use those for kind of geochemistry. It has low rates of diffusion for most elements, so zircon will survive many thermal processes without changing its chemistry, and is chemically and mechanically resistant. So it's not quite lasting forever, but it will last a very long time. Well, this is up. Let me just tell you that everything I'm going to say today, almost everything I'm going to tell you today, is as relevant for zircons that are smaller than the eye can see. Everything we do is in the 100 micron to maybe 200 micron length range. So these are less than a millimeter. I have rarely seen zircons larger than that, so I'm very intrigued about looking at larger crystals that we've seen in the slides so far today. But that's a different world from everything we've done. Everything we've done is focusing on small zircon grains. So these are some of the reasons why zircon is so interesting these days. Certainly in red, you can do uranium lead geochronology, and that'll tell you when that crystal actually formed. You can do the next two green ones there. You can do uranium, thorium, helium thermochronology or fission track thermochronology. That tells you its cooling history. You can use lutetium hafnium isotopes to talk about the crustal genesis, the environment in which that zircon formed. We'll talk a little bit about that today. The next two, oxygen and lithium, they tell you about interaction with fluids. Samarium, neodymium, RBSR, lead isotopes tell you something about the petrochemistry, how that zircon crystal formed. And then today we'll talk a little bit about trace element, petrochemistry, and rare earth elements, what they can tell you about the geochemistry of the environment in which that zircon was forming. So I'm going to do three things in my talk today. I'm going to do the basics of how the geochron systems work, and then I'll talk about some applications for earth science. And at the very end, I'll talk a little bit about relevance for gemology, but this is not something I know a lot about. So I'm really interested in hearing kind of follow-on conversation about how geochron can be applied to gemology. So this is the playing field that we have, Zircon ZrSiO4 in blue. And we're going to use the uranium, thorium, lead system in orange, uranium, thorium, and lead. We also measure mercury because mercury has an isotope that interferes with the measurement of lead-204. We'll talk about lutetium, terbium, hafnium isotopes. We'll talk about trace elements, and these are some of the ones that are high enough concentrations in zircons to be able to measure them, and then the rare earth elements. And we'll work our way through these different chemical systems during my talk today. So here's just a very quick plot showing the abundance of these different elements relative to chondrites, sort of average crust of the silicate earth. And what it shows is from barium to phosphorus here, just the concentration of these different elements. And so here's thorium, here's uranium, and here's hafnium, the three main elements that we're going to be using to characterize the age and chemistry of zircon. Here's a plot that shows how we measure them. I'm going to be talking mostly about laser ablation Icpms. You can't really do very much of this with an SEM. Here's the limit of detection for an SEM, so you can only see the major elements that are present within that crystal. If you do it with a microprobe, WDS, you might be able to see half of the elements that are present in zircon. Raman is down here, kind of a new field, new way of looking at the chemistry of zircons. And for laser ablation, our limit of detection is down here, where we can see most of the elements that are of interest for zircon, but not quite all. Lanthanum is one we'd really like to see a little bit better, but it's usually concentration is too low. We're going to talk about radiometric dating, so let's go back in history a little bit. Of course, this comes back to Marie and Pierre Curie in the late 1800s. Her PhD dissertation was on uraninite, where she first was able to document the radioactive decay of uraninite. And so we're using that same decay system. To jump into a first order application, Clara Patterson, professor at Caltech, who I had the pleasure of overlapping with a little bit when I was at Caltech, was the first person to determine the age of the Earth. He did this by looking at the Canyon Diablo meteorite, one of his ways of doing this. This is the meteorite that struck a meteor crater in Arizona, if you've been there before. And he dated that troilite crystal using the uranium lead system and came up with an age of 4.5 billion years, which is still pretty close to the age of the Earth as we recognize it today. Interesting story about this, and one that affects us in our everyday lives. Dr. Patterson had a very difficult time measuring the lead in his samples because there was so much lead in the environment. He began to wonder where all that environmental lead was coming from. He would have to spend a lot of time without shoes, without clothes here in his lab, scrubbing his lab, trying to remove all that environmental lead. He became curious about where all that environmental lead came from and determined that it was from the lead that had been added to gasoline. And so you may know this history. The green curve here is the births of people in the US. The blue curve here is the concentration of lead in gasoline, the amount of gasoline that was sold. And the red curve here, this is the concentration of lead in blood samples that were collected during this time. 1973, that he finally convinced the EPA to ban the addition of lead in commercial gasoline. And what you see is that the lead in gas dropped soon thereafter, and the lead in blood of US people dropped very soon thereafter. And of course, that has huge impacts for public health. We can owe our longevity in part to Clara Patterson. So let's go back to King Zircon here and talk a little bit about the decay systems that we're going to be using for the chronology of zircon. So there are two uranium isotopes, uranium-235 that decays to lead-206, has a half-life of 4.5 billion years, just by coincidence, about the same age as the Earth. Uranium-235 decays to lead-207, shorter half-life. That's going to become apparent in just a minute. And then the third radiogenic parent, thorium-232, decays to lead-208, and that has a very long half-life. So you can see the half-lives here are great for studying Earth processes, maybe not so great for studying human timescales, but great for processes within the Earth. The cool thing about these decay systems is that because the concentration of 238 to 235 is fixed in nature, these two chronometers, the top two, behave pretty much in tandem. It's kind of like on your wrist if you have two watches and they're ticking at the same time but at a slightly different rate. You can look at your two watches, and if they agree, then you'll say, oh, I have good confidence that the time is really what those watches are showing. And so we're going to take advantage of those two different chronometers, and we're going to plot them on a single diagram. It's called a Concordia diagram. You may have seen this if you've looked at papers that report uranium lead data. On the y-axis is the parent 238 decaying to lead, so daughter over parent. It's going to increase in time. On the x-axis is daughter 207, parent 235. It's also going to increase in time. I'll show you that in just a second. I'm not going to go through these in detail, but if you ever want to look at how this actually takes place, this is the decay scheme for uranium 238 decaying down to lead 206. Fortunately, it's a very simple decay system, no branching decays, and only one rate controlling decay system here. Same thing for lead 207 coming from 235, a single decay chain with a rate controlling decay right here at the start. And same thing for thorium. So decay-wise, it's a pretty simple system. Other chronometers have maybe a more complicated decay scheme than uranium lead, so that adds to its simplicity. If you know how the radioactive decay systems work, you may have had to derive this equation at some point. Here's what you might have done recently. If you're in a bike race, you know how many people are in the race. You know how many crashes take place. If you listen to your spouse or your parent about the probability of a crash taking place during this race, maybe they're not so excited about you doing this sport. That's all you have to know to calculate the length of that race, how long that race took, how many racers, how many crashes, the probability of a crash. That's the decay constant for radioactive decay. And you can calculate the duration of that race. So just an example of how the decay system works. We'll do this kind of quickly because I know this is kind of under the hood for you. But it's pretty simple. Let's take a look at the left one over here, uranium 238 decaying to lead 206. At time zero, maybe 4.5 billion years ago, we're going to form a zircon crystal. There's going to be a lot of uranium. There's going to be 0 lead, because zircon does not include very much lead when it forms. Over time, one half-life, half of that uranium is going to decay. It's going to decay atom by atom to lead 206. And so at the end of 4.5 billion years, you'll have equal atom, daughter 206 and parent 238. This decay system is much faster. This has a significant curve to it, and that's why our Concordia line has a bit of a curve to it also. And it turns out that this is a powerful aspect of our two chronometers, is that they're ticking at very different rates, and so they're affected by different processes. So what we're going to see is how they behave together on this Concordia diagram. We're going to crystallize a magma, crystallize some zircon here at time zero. We're going to come back 1,000 million years later, 1 billion years later. We will have formed from some 206 from the decay of 238. We'll form from some 207 from 235, and we'll end up on Concordia. We let our watches tick for another 1 billion years. They're gonna move together in coordination, and we'll end up on Concordia out here. You come back 2.9 billion years after crystallization, and they'll both sit on top of Concordia. This is in a simple system. This is what I would guess is the case for most of the high zircons that Ray mentioned. I've never heard that term before, but if a zircon is simple and your two chronometers tell you the same time, my guess is that that's a high zircon. Those two systems have not been disturbed. There are 3 main processes where you can take an analysis of zircon off of the Concordia line. This is now getting into the complicated world. My guess is that this is where most of those medium and low quality zircons that Ray referred to reside. So one way we can do this is we can start off with a zircon. It's 2 billion years old. And right now, today, we're going to hit that zircon with some hydrothermal fluids, especially if they're 300 to 400 degrees. That seems to be the main temperature at which lead is mobilized. And it's probably this process of becoming metamict is involved in that. And what we're going to do is we're going to leach out some of the 206 and some of the 207. It works usually that the smaller zircons are going to lose a higher proportion than the larger crystals. That's just the surface to volume of the zircon crystal. Small crystals have higher surface, lower volume, and so they lose more of their lead. And they end up down here in this Discordia space. So the magic of this Concordia diagram is that if we now let the system get 1 billion years older, we're going to end up with our original zircon crystal here. These are the zircons that have lost lead, and they're going to come down, and you can actually get the age of that lower intercept here. That would be age of hydrothermal activity. So from a zircon crystal, you can actually get 2 ages for the price of 1, the crystallization age, and then the lower intercept age. So I didn't spend a lot of time focusing on this in the presentation, but you may be surprised to know, but this is what your zircons look like on the inside. If you were to slice them and do a CL image, I would guess that almost every crystal you see looks like this. It has tremendous zonation. We can use this zonation to tell us something interesting about the growth history. My guess is that this nice igneous zonation is going to be up here on that undisturbed line. This is metamixed hydrothermal zircon in here. It's probably going to sit down here. If you were to analyze the whole grain, you would probably get this kind of a mixing array. So here we have a crystal. I would guess this is high zircon, this is high zircon. I'll bet that's low zircon, and this is probably medium zircon. So check that out. Each crystal probably has different domains of that quality index. Most zircons also have multiple growth histories. I would say very few zircons grew just in one phase. Here's one where we first formed this zircon. This is kind of nice igneous oscillatory zoning. And then that crystal was overgrown by a younger formation of zircon. And so this has a very different age from this one. We call this inheritance. So what we can do is we can put a spot here. We can analyze this older material. It might be 2 billion years old. We put a spot in here in this younger material that's just growing. And so we see kind of schematically here, usually works out that the older zircon is in the middle and the younger zircon grows around the outside, just like a tree ring, just like tree rings. And then the cool thing is on the Concordia diagram, these 2 lines move out in space together. So here's our original zircon, 3 billion years old. Here's that younger rim, 1 billion year old. My guess is that many of your gem quality zircons have this kind of a growth history where there are multiple phases of growth. Another typical thing that happens in zircon is that they are overgrown by metamorphic processes. And so here we have an original zircon in the middle that grew in a magma. It's igneous zircon, and it's overgrown by this metamorphic zircon. In CL images, we can see that to be the case. And now we can do an analysis of the interior spot, get the age of the igneous material, do an age on the metamorphic rim, and get that younger rim. And then you can get 2 ages for the price of 1 here. My guess is that this crystal would also be down here in this Discordia area. Maybe optically, it would be a medium or low quality zircon crystal. But that's the fact of life. About maybe a half of the zircons that we analyze are complicated by these processes of lead loss or overgrowths or metamorphic rims growing around them. Let's talk a little bit about how we determine these ages in case you ever have a chance to get involved in doing some geochronology. There's different ways that we can determine the ages of interest. And what we're interested in is measuring 2 uranium isotopes, and we're going to measure 4 different lead isotopes. With a mass spectrometer, it's easy to measure the isotope ratio of just lead. They behave very similar chemically in a mass spectrometer, whereas lead versus uranium behaves very differently. They're fractionated by about 10%. And so if you analyze a zircon crystal really with any method, you're probably going to get a uranium lead 206 to 238 age that's probably about 10% off. No matter how much you spend on your mass spectrometer, you're probably going to be about 10% off. So of course, we have ways of correcting for that fractionation. And these are the 3 instruments that are used for doing uranium lead geochronology. This is kind of the original instrument that was used. It's a thermal ionization mass spectrometer. When you want to use this technique, it gives you very high precision ages. but unfortunately you have to dissolve that whole crystal. And so you might lose any of that information about the zonation in the interior of the crystal. You get the average age. And because that zircon has been dissolved, we can add a spike. We had a spike of 205 lead and 233 uranium. Those are not naturally occurring. So then we can just measure the concentration of those spike elements relative to the naturally occurring ones. This is a pretty expensive process. You'll probably pay about $100 for each age that you get using this technique, but the precision is quite impressive. More likely, if you do uranium lead geochronology, you'll use one of these two instruments. Laser ablation Icpms is the main instrument that's used these days, or you might have access to an ion probe. There are fewer of these in the world, and they're much more expensive and much more difficult to maintain, whereas there's hundreds of these laser ablation Icpms labs. In this case, we're going to hit the zircon crystal with a laser beam or with an ion beam, and we'll be able to focus in on just a particular part of that crystal, so we get that spatial resolution. But we can't add a spike, so what we do instead is we compare the age of our unknown with another crystal next door, which is the age of a standard, and we know the age of that standard, and we just go back and forth, standard, unknown, comparing those two. We call that standard sample bracketing. So let me show you a couple of pictures here. This is an Icpms lab. If you live in an Icpms lab, you will wear a bunny suit most of the time. Your life depends on Teflon. It's the only material that's clean enough in terms of lead concentration that you can handle the solutions from a dissolved zircon. It involves lots of ion exchange, a lot of heating and evaporating. It's a very time-consuming process. It's expensive, but you get really good accuracy with those ages. Here's a picture of the two different types of ion probes. This is in Russia here. They have one that's called a shrimp, also many in Australia. This is a Kamika ion probe, and you can just see that these are complicated instruments. They take a lot of care and feeding to keep them working well, but they have amazing resolution. You can actually strip off atomic layer by atomic layer of a crystal and kind of do that spatial resolution with very high precision, individual atomic layers coming off. To do this, we need to do the standard sample bracketing. So here's some unknown zircons, and here's some of the standards that we use. I'll talk about those standards in just a minute. Here's how we do this with laser ablation. It's a much simpler machine. It's probably about $1 million investment to have a laser ablation instrument, as opposed to $5 million for an ion probe. Two machines, the zircon sits in here in the chamber of the laser. You'll see a video in just a minute here that kind of shows you how the instruments work. The important aspect of the laser chamber here is this little cup that sits above your sample. The laser beam comes right down the middle. It flashes away on your zircon crystal right here, and then that material is carried in helium gas down this tube, and it goes into the mass spectrometer. This is actually a big problem for us right now, because most of the helium in the world comes from Ukraine, and that supply has pretty much shut off. We're paying exorbitant prices for helium right now, and we may run out here soon. That helium then goes into the plasma torch of the ICP mass spectrometer. Plasma is up at a temperature of about 6,000 degrees. It's very effective at ionizing the different elements that are coming off. So we get charged ions, which can then be accelerated down the mass spectrometer, which separates them by mass. It's a mass spectrometer, so that's what it does. And then we can measure the different isotopes of uranium and lead that way. Hey, some zircons. These are actually big enough that you can see. These are some of the standards that we use. These are from Sri Lanka. I have a nephew who's an anthropologist in Sri Lanka. He can get into the gem pits, and he's been able to send me many of these really nice large crystals of Sri Lanka zircon. So those are one of the standards that we use. We know the age of the Sri Lanka zircon is about 557 MA. But we like to look at samples that go the whole range of Earth time, from 4.5 billion all the way to the present day. So we analyze many other standards. You probably have not heard of many of these. OG1 from Australia, Tan Brown from India, QGNG. These are just zircons that have been well characterized for their age. Oracle from, you might have heard of this one. This is the Harvard zircon. It's a large crystal, and it's probably the best characterized zircon that we know of in the world. Pesci from Brazil, Sri Lanka, R33 from New Hampshire, Tamora from Australia, Plizovici from Czechoslovakia, GHR from Washington, Fish Canyon from New Mexico. So with every analysis of unknowns, we analyze all of these different standards just to make sure that we're doing the fractionation correction accurately. So standards are a big part of what we do. The Sri Lanka zircons are the only big ones. All these other ones are small, sub-millimeter crystals that come from rocks. And that's actually advantageous because it turns out that each one of these Sri Lanka zircon crystals has a slightly different age. We characterize this one here, Sri Lanka F, very well. And unfortunately, we're pretty much out of it. And so now we have to go through the trouble of calibrating a second crystal and distributing that to other people in the world. Here's just very quickly, you're going to see this in a video in just a minute, but here's how an analysis works. We spend 15 seconds with our mass spectrometer on with no laser firing. We count the background intensities of 238, 232, the lead isotopes that we're going to use to calculate the ages. We fire the laser, and uranium has the highest intensity. You can see the intensity of the other elements. We do that about 15 seconds. We turn the laser off. And then we have 30 seconds where we can look at the age, get excited about what it means for us, and then we're ready to start doing the next analysis. So that's kind of the basics of how the process works. Let me show you, I just put this in before the start of the presentation to show you a little bit about how we image crystals. And now after seeing the kind of gem quality zircons you look at, I'd like you to know that this is what the interiors of zircon crystals look like. We look at them with the SEM in 3 different ways. We first look at the outside morphology. And these, you're saying, well, wait a minute, they're all rounded. That's because these are detrital zircon crystals. They become rounded and spherical as they move down a riverbed or as they wash back and forth on a beach face. We look at them to characterize their shape. We then look at them with a backscatter image, and you can see a little bit of zonation in here. That tells us a little bit about the chemistry. It also allows us to make sure that we analyze a zircon and don't analyze something else like magnetite that might have a lot of common lead in it. And then we do CL images, and these are just kind of typical images of zircon. These are not unusual in any way. The lower right here, this is one of my favorite zircons. Each of these little red rings here is an analysis that we've done, and we've been able to imprint the age of that crystal onto the CL image. And it looks like this has 5 different episodes of growth. So zircons maybe last forever, but they grow in sequence over different times, starting in this case 130 million years ago, growing in several different phases with different properties of uranium and their chemistry, and then a little rim here that grew 57 million years ago. My guess is that many of the crystals that you are using for your gems probably have this same very rich growth history that would be fascinating to characterize. Let me take you on a little tour through our lab. I'm going to bring you to a YouTube channel from the Lasercron lab. And this is it's kind of a promo for our lab, but it kind of shows you the different processes that we go through. And I imagine that these processes are very different. You wouldn't want to do these processes to your gem samples, but let's dive in and just kind of work our way through how it works. Well, of course, we have to watch the ad first.
Chart full of features that allows you to work your math.
Yeah, we can't see the video there. I think we need to change the screen share to share the actual YouTube.
We're here in the beautiful Sonoran Desert, just west of camp.
Okay, I was hearing someone say you're not able to see the video.
Yes, that's right. You need to do a new screen share from the video.
And we're here in the beautiful Sonoran Desert, just west of camp. And we're going to show you the rock to getting a final age in the lab. So this is the Ryle.
Okay, sorry. Could you tell me if you're able to see the video when it was?
All the steps from collecting the rock
Not
to
yet.
getting a final age in the lab.
Yeah, I think you have to stop the screen share and start it again with the video.
So the key is where it comes a small bag like this. So the
We
key
might
is
have to skip the video, George.
the size of your fist. That's it. Last rock. Let's go get an age. Hey, I'm Martin Pepper. Just remember,
Wow, I had to close everything down. So you were not able to see the video when it was enlarged? Is that correct?
No, because it was just showing the PowerPoint still.
Okay, let me fire this back up again and let's see if we can get this right. Sorry for the IT glitch. Let's go back to this.
For the sake of fluidity in your presentation, it might actually prove to be better to move forward if you don't mind, George.
Okay, let's do that. Yeah, and we're going to run out of time here, so let's keep going. So you're able to see the slides now again?
Yep.
Yeah, that's fine.
Good. Okay, so let's press on. These are a little bit about the applications of Zircon geochronology, and we're going to put this into our sort of view of tectonic processes of magmas being generated in a subduction zone where crust is going down underneath the continent. Magmas are rising up through the surface, and your zircon crystals are probably forming within one of these magmas or maybe along the margins of those magma bodies. And so these are just kind of snapshots of different applications of how we can use the ages of zircon crystals. So one, of course, process is to determine the growth history of continental crust. Most of continental crust is made up of rocks like here in Yosemite, granite bodies that contain maybe 0.1% zircon, trace amounts of zircon, so we can determine the age of that continental crust. Ore deposits commonly form along the margins of these plutons, these magma bodies as well, and so zircon can tell us something about the age of those ore deposits. That turns out to be a very effective strategy for exploring. It turns out in many parts of the world, only magma bodies of a certain age contain certain types of ore deposits. And so zircon dating is a very effective exploration strategy. Volcanic history, of course, nowadays we're very interested in predicting volcanic eruption potential. And we do that by looking back in the past and saying something about the likelihood of eruptions in the future. Zircons would be present within this ash material as well as the lava flows coming down. So zircon can be present in any of those rock materials. Sometimes those ash layers like this accumulate in a sedimentary basin where other types of sedimentary layers are accumulating. And then we can determine the age of that ash layer and say something about the age of the sediment above and below. Of course, the sediment below would be older. The sediment above would be younger. In many cases, those sedimentary layers contain fossils that we're interested in the age of. So this is one of the main ways that we've calibrated the pace of evolution in Earth history is by dating those ash layers with uranium-lead geochronology of zircons. One that has received a lot of interest is the boundary between the Cretaceous and the Tertiary. This is the time when dinosaurs went extinct. So in sediments older than this layer, we see dinosaur fossils. In sediments above that layer, this very thin layer, the dinosaurs were completely wiped out 66, 65 million years ago. And we know that history from zircon dating of ash layers along that boundary. This is sort of the pace of evolution. Many of the organisms that we see on Earth today can be traced back to the Cambrian period, about 500 million years ago. And one of the spectacular aspects of this evolutionary history is that there have been several major several major extinctions. End of Cretaceous, this meteorite impact here. End of the Permian, probably the biggest extinction. We know a lot about that one now because of very precise zircon dating from the end of the Permian. So we can look at the pace of these evolutionary changes in life on Earth by doing this zircon dating of sedimentary rocks and their fossils. One of the main applications these days of detrital zircon, of zircon dating is looking at detrital zircons, sedimentary zircons. So for example, in the Amazon River, we can look at ages of zircon crystals from along the length of the Amazon River, and we can say where those zircons came from in the Andes Mountains. We can do provenance work, and we'll talk a little bit more about provenance of zircons in just a minute. This is a technique that's fairly recent. It's only been around for about 15 or 20 years. It's probably one of the techniques that's really driving the rapid growth of zircon geochronology. We can also do this back in the past. If you are interested in the Navajo sandstone here in northern Arizona, we could take a piece of Navajo sandstone, look at the ages of zircons, and big surprise, most of those zircons actually came from the Appalachians. Zircon is a very resistant mineral. We think that back in Jurassic time, there were rivers coming from the Appalachians, coming all the way across North America. The trade winds were blowing these zircons into these sand dune deposits of Jurassic age. And so we can reconstruct where each of those zircons came from by knowing the age and knowing the ages of rocks in the Appalachian Mountains. We can look at things like collision of India with Asia, where the Himalayas are formed. Many of the gem quality zircons that you are interested in come from magmas that were generated during this period. Lots of pegmatites were generated. And so what we can do is we can look at the ages of rocks, zircons and garnets in the Himalayas. And then we can look at the ages of crystals that we find in the sedimentary horizons out in the western part or the southern part of the Himalayas, and talk about when these rocks were first brought to the surface. So the history of that mountain building period. We can look at the ages of magnetic reversals. Your magnet now in your compass now points to north, but in the past it had pointed to south. Various times in the past, our magnetic field has changed. And so we can look at this history, and it turns out to be very relevant for life. Many of the big changes in life, when you go from very primitive life to the present day, many of these extinction events coincide with changes in the magnetic polarity of our magnetic field. So people are very interested in when that next magnetic field reversal is going to take place. It's also very important for studying climate change. This is just a curve for the last 500 million years of our climate going through hot and cold periods. Of course, this is what's happening right now. And we're very interested in what the future of that curve looks like. The way we do that kind of science is by looking back in the past, seeing how the Earth has recovered from these times when there have been high concentrations of these greenhouse gases. And we get that information by dating rock layers that contain these archives of climate information. One of the really exciting and probably really important aspects of zircon chronology is that the oldest rock on Earth is 4 billion years old, whereas we know the Earth formed 4.6 billion years ago. The only mineral record, the only record we have on Earth of that first 500, 600 million years of time is from zircons. Out here in the Jack Hills of Western Australia, in these sedimentary layers, there are zircons that have been found that go all the way back just about to 4.5 billion years ago. And a lot of people have spent a lot of time looking at those Jack Hill zircons. What they have found in those zircons is little magnetite inclusions. Even though the crystals are very small, we can analyze just the inclusions within those zircon grains. We now know that the Earth had a magnetosphere going all the way back, probably to 4.3 billion. We know that the Earth had an atmosphere and oceans by looking at the oxygen isotopes in those zircon crystals. We think that continental crust existed. The Earth went very rapidly to a mode kind of like we see today, where there's continental crust and oceanic crust. We can look at carbon isotopes and talk about the presence of life. These are some of the zircon crystals from the Jack Hills quartzite. While I'm showing these nice red crystals, I should tell you that we use color a lot because we can actually tell the age of a zircon crystal by looking at the color. In my experience, if they're 0 back to about 500 million years old, they're generally colorless. As they get back to about 1 billion years old, they turn slightly pinkish. If they're 2 billion years old, they're usually kind of a moderate to deep pink. And if they're 3 billion years and older, then they have this dark kind of ruby, even purplish tint to them. So I'm very interested to learn more about all the colors of zircons that you're observing in our world. It's clear, and then they get pink to purplish with age as that radiation damage has affected the crystal structure. I'm almost done here. I know I'm going a little bit longer. Let me just offer a few thoughts about relevance for gemology, and then I'd love to open it up for some more conversation. These are just some aspects that I know very little about. Of course, we can look at the chemistry of zircons to talk about the color, the original color, and the treatment that has taken place. And then the one that I'm most interested in is to tell something about the provenance of zircons. And so I'll just talk about some of the other elements that we measure in zircon. In addition to their age, we can look at their hafnium 176, 177 isotope ratio. The hafnium is quite abundant in zircon. And we can see, for example, in Australia, that as time goes on from 500 million years ago to 250 million years ago, zircons have this interesting pattern of more negative hafnium values, more positive values. And so if you were to bring me a zircon crystal from Australia, I could measure the hafnium isotopes and I could probably tell you which of these different igneous bodies that zircon came from. A little bit about the crustal history and maybe provenance. This is just an example of the use of some of the other trace elements, scandium-ytterbium ratio versus niobium-ytterbium. We can say something about the environment, whether it's a continental volcanic province, something like Iceland, if it's oceanic, say something about the origin of that zircon based on its chemistry. We can actually tell you the temperature of crystallization by looking at the titanium concentration in zircon. And using modern rocks as an example that we know the temperature of crystallization from, we can actually reconstruct what the temperature was when that zircon crystallized. And it's usually between about 600 C and about 1400 C. That's the range of this thermometer. We can actually look at modern arc systems where magmas are forming today, and we know the thickness of the crust. And it turns out that the lanthanum-ytterbium ratio, two rare earth elements, that chemical ratio is also a function of the thickness of the crust. And so just an example here, the Sierra Nevada, we can date zircons, we can look at the lanthanum-ytterbium ratio, and we can tell you how thick the crust was, 50 kilometers, 60 kilometers, 70 kilometers at the time when that zircon crystallized. So we can back out a lot of information about how the processes were operating when the zircon formed. We're just starting to look at these other rare earths. This is just an example of some of the rare earth patterns that we see in some of the standards that we've looked at. And I would guess that many zircons are going to have very different rare earth patterns that we can use to talk about their origin and their provenance. I did do one interesting example. This is really my only experience doing gemology. I happened to be able to team up with Bruce Bridges, who has these Tsavorite crystals, and he was very interested in the relationship between the concentration of the crystals and the color. These are his color terms here. And his thought was that the color of these crystals has to do with the vanadium chromium ratio. And so in our laser ablation Icpms, we put in his beautiful crystals here. He asked us to put our pits into the girdle, which we were able to do, even though they're so small, you wouldn't be able to see them. We did do it just on the sides of the crystals. And it turned out that there was sort of a general correlation that the lighter crystals tend to have higher vanadium, the darker colors tend to have lower vanadium, higher chromium. So it's kind of an interesting experiment that confirmed what Bruce expected. But here's something that we did with his Tsavorites, which we didn't expect to see. And this is looking at raw Tsavorites from two different mines. There's one called the Scorpion Mine and one called the Zircon Mine. And it turns out that even though they have very similar colors, they have very different vanadium chromium ratios. These are all less than 1, and these are all up around 100. So this is interesting. It's not just the chemistry that controls their color, because their color is very similar, but they have very different chemistries. There's something else going on. So we're hoping to do a little bit more work with Bruce on these Tsavorites, and we'd love to work with other people on zircons to see if we can do the same kinds of characterizations and maybe do provenance like this, where we're able to identify a particular mine that one of these crystals came from. And this is one of the slides in the video that I didn't show you. I was going to show you, but this is our lab manager showing a rock that we took zircons from. And all these little pins here, these are the samples that we've analyzed from around the world for zircon geochronology and chemistry. In the last 10 years, we've probably done 5 million analyses, probably from about 100,000 samples, maybe from 1,000 localities around the world. And what we're hoping to do is build up a database of all the zircon ages and chemistry from around the world. And then the hope is that people would be able to bring us a zircon crystal, maybe a gem. We would be able to characterize the chemistry and then relate it back to a particular place around the world, sort of verify the provenance of those crystals. And I know that's something of interest to people in the gem world. So I'm going to stop sharing there, and I'm going to open it up for any questions that people have. And I'm sorry if that went a little fast and a little long.
Yes, I have a question, and it might be a dumb question, but I'll ask it anyway. I don't know anything about chemistry, but what you've said about being able to use the zircons to date on Earth, if you take into account the fact that we have the atmosphere, oceans, and most importantly, life, would you, well, for one thing, I forget what you said about the chemistry of zircon itself. Would something like a zircon exist on Mars? And if it did, given that the atmosphere, oceans, or lack thereof, and potentially lack of life, would you be able to use them to date? And if there aren't zircons on somewhere like Mars, would there be a next best thing? Like on Earth, is there a next best thing if you didn't have zircons?
Yeah, a couple of different questions. On Earth, there are probably a dozen different minerals that we can use for uranium-lead decay. That's what we need to do geochronology with those systems. And there are other minerals that we can use: titanite, bedeliite, monazite, xenotime, rutile are the main ones that we use. And any of those minerals can tell us time. We actually don't know as much about the chemistry of those other minerals. They're kind of next up in terms of characterization and trying to develop them as geochemical indicators as well as chronometers. So zircon is king right now. We've done most of the work on zircon, but next up are these other minerals. With respect to other planets, we would just need a planet that has a silicate crust or a silicate history to be able to get zircons. I think most likely on Mars, there's probably not going to be very much zircon. There's probably going to be bedeliite instead. I'm not sure if you Gem folks would be familiar with bedeliite. It's a zirconium oxide, and so it would occur in intermediate to mafic composition rocks that have lower silicon concentrations. Bedeliite is another one that we're just exploring now for chemistry. So my guess is if we can't do zircon, we're probably going to be able to do bedeliite on other planets. I've been exploring that a little bit, and what people tell us is that it's so difficult to bring samples back from other planets. What we need to do is develop a mass spectrometer that we can fly to Mars or to Jupiter or to Venus and do our analyses on site. So something for the future, a mass spectrometer on a spacecraft.
I think
Thank you.
Bob Downs on Curiosity has an X-ray spectrometer as well as a Raman to do identification, and then they're using Earth-based standards to compare the data. So the other question, I had a quick one for you, please, George, before we move on.
Before you run off on that one, just to mention, yes, there are zircons from Mars. We have already analyzed zircons from Martian meteorites. The NWA 7034 meteorite is one, for example. They've found that they've analyzed at least 60 zircon grains from that one. 4.48 billion years old in that particular one. Anyway, sorry, Ray.
Just a quick question about certolite zircons, which are, to my knowledge, very radioactive, and yet which would make them very lows in terms of zircon designations, and yet they seem to have very well-formed crystals. So it seemed to be some kind of a conflict there in terms of designations and understanding. So have you worked at all with certolite zircons?
I'm embarrassed to say I wouldn't know if I had. I'm not sure that we would be able to tell that difference.
Not to worry. It was just there were certolite zircons found on the Silver Crater mine in near Bancroft, Ontario, and so and they were very distinctly crystallized. Anyway, look, I'm thanking you very much. That was an interesting presentation, and I think more important was your correlation of what you do to what we're able to learn in terms of world history and development and all the abilities of this system that you're doing, although quite expensive per test, to be able to ascertain origins. I think they're moving along with Raman to do something similar to try and find origins. So technology is advancing so quickly, and we're glad we have people like you, George, who are at the forefront, making it known and learning more. So thank you for your contribution today. And oh yes, Antoinette, you're muted.
I have a self-serving question. Since you are in Arizona, George. And the Big Tucson Show is held every year in Tucson. And the Accredited Gemologists Association, which is independent gemologists from around the world, I'm thinking that there might provide an opportunity either just before or just after the show for you and some of us to get together and talk about ways in which we might be able to provide you perhaps with samples you don't have, or work together to find out where and what information the two of us could glean together that would benefit both you and us, because I think there's a lot of fascinating things that would add to the story of gems that we don't yet know. I found this whole thing really fascinating, and I know everybody else did too. And I just think it would enrich our understanding of the broader field of rocks, minerals, gems, and their message, their story about our very planet and others in outer space. So would you consider that? You don't have to answer now. They know how to reach me here. So we could do it by email or some such thing, or telephone. I actually like telephones, guys. It shows my age, but anyway, I'd love to talk to you about it.
I'll just answer with a very quick yes. I would love to do that. We're planning to do that now with our new mineral museum here in Tucson. If you've been to the Gem Show recently, you know we have a new mineral museum
Right.
in our department. We actually have a professor of gem science, Ananya Malik, just on the scene this year. So I'm really hoping that we can kind of merge our interests and apply what we do to the wider world of gems.
Yes. Well, I was sorry I didn't get to Tucson this year due to the pandemic and illness, but next year is a new year. So I look forward to it.
Thanks
And
so
to
much for
talking
your
to you
question,
before.
Antoinette.
Very
And I look upon this as, and I've wanted it to different people, that this program is to try and encourage geologists to find an interest and curiosity about gems, and have gemologists and appraisers have an interest in growing knowledge of geology. That's why we include those both portions in every program. So
Exactly.
thank you for your contribution, George.
Yes.
And finally, but not last but not least, we have Daniel at 3 or 4 in the morning for him, God bless his soul, going to present to us a little bit about a very special trip he made, which I am so jealous of, to Cambodia. But just to give a little bit of introduction, Daniel, he is no small potatoes when it comes to fasting. He is a Grand Master Faceter, and that's one of the highest designations the United States Fasters Guild will present to someone who is talented in the field of faceting, and he is that person, someone who's talented. He's developed and created a machine called the Dream Fasting Machine, which if I was to learn fasting again now, I probably would want one of. And he also teaches faceting, and I again would want to be one of his students, because he and his students have won some of the top honors with the highest scores since very early 80s in US and Australian faceting contests. So he's no slouch. And he also knows his stones as a byproduct of all this. So we're very happy to have a few minutes of Daniel's time so early in the morning to tell us a bit about his experiences. And by the way, he also was founder of the Taiwan Geometric Fine Gemstone. So this guy's got his fingers in a lot of pies, and he certainly has good knowledge from the ground up, because I found that faceters who take an interest in gemology really may be the most knowledgeable ones out there, because they see it all. They see how the stones hold together and how they fall apart, and what they can do to make them look better is part of an art and a skill, which I admire greatly. So without any further introduction, please, Daniel, can you share with us about your trip into Cambodia?
Thank you. My name is Daniel. Hello. And because right now I'm in Shanghai for business trip, and then the connect is very weak. Actually, I just can see the lake view picture on the computer picture, and then I just asked Jordan for help, because I just record a whole video. So maybe Jordan, that you can help me to play this video, okay? And that's the whole complete presentation.
Okay, here it comes. And then obviously you'll be here still live to answer questions afterwards.
Yeah. Since I was a child, I have no resistance to shiny things. I'm very lucky. Now I have become precision faceter and turned this love into my career. Unlike commercial cutter, precision faceter are usually sick. We pursue perfection, let the light reflect in the gemstone accurately, and show its gorgeous beauty. In 2017, I became a full-time precision faceter, began to develop faceting machine, Dreamer, and a teaching system. In these 5 years, my students and I joined USFG SSC, an international faceting challenge, which organized by the American and Australian faceter guilds. We won the first place at each levels for many years. It shows the achievement of our faceting machine and teaching system as well. Following pictures are our stones and medals of the competition. However, today we are not talking about the skill of gem faceting, but another important ability, rough hunting in the mine. In this episode, I will take you into Cambodia to find beautiful zircon. Before we start this episode, I will briefly introduce the basic knowledges of natural zircon. We will start from Phnom Penh, the capital of Cambodia, then go to Ratanakiri province and enter the zircon mine. When we arrive at the mine, I will use the perspective of faceter to show you the process of zircon from rough to cut stone by videos and photos. The chemical formula of zircon is zirconia over silicon. In the classification of zircon, it can be divided into 3 types: low, intermediate, and high, according to the radioactive damage to its crystal structure. Cambodia zircon belongs to high-type zircon with the least radioactive damage. Its specific gravity, refractive index, and most hardness are the highest among all 3 types, and has strong birefringence. Cambodia zircons are also one of the few zircons that have the opportunity to change color from reddish brown to blue by heating. Great. Let's start from Phnom Penh. Phnom Penh is the capital of Cambodia. There is an Art Deco landmark called Center Market. The bright yellow building, complete in 1937, has a 26-meter high center dome. When it first opened in 1937, it was said to be the biggest market in Asia. You can find many booths selling jewelry and gold in this place. But please be careful, especially when you are unfamiliar with the quality and market price. This is the most important thing to pay attention to in any trading market. Usually, we'll stay in Phnom Penh for one day to find a local fan that will leave for Ratanakili the next morning. We can also take local delicious snacks and try to get some supplies. The road is more than 500 kilometers away. No highways and needs to take 7 to 8 hours. So, it usually starts in the morning and arrives in Ratanakili province in the afternoon. Ratanakili literally means Gemstone Mountain in Khmer, the language of Cambodia. The area consists of overlapping debris fields, of many small volcanic eruptions ranging in age from 700,000 to 2 million years. Now, rubber and black pepper are the main scale agriculture in this area. The first photo shows black pepper dry on the ground, while the second photo shows local pepper trees. Next, we will briefly introduce the Zircon mine and how miners enter the mine to work. Zircon mines in Ratanakili are small-scale gem-quality stones. They are found in the red sandstone soils from weather basals. These gemstones are mined through a shaft with a diameter about 1 meter, depth about 3 to 6 meters, and length about 5 to 8 meters. Some longer channels will dig another shaft to get enough air. This is Zircon mine digging under the rubber trees. How to transport and separate rough from soil. In the shaft, the miners dig with a sharp long steel bar. Set up a windlass above the shaft on the ground and drop the bucket to load the soil. These workers are usually Aboriginal people. As you can see, due to the soil types and the shortage of water resource, miners can only separate zircon rough from the soil by hand. In fact, only a very low percentage of zircon rough are actually valuable as gemstone. How does miner get into the shaft? In the video, you can see how miners move their body in the shaft with their elbows through the concave on the left and right side of the shaft. In fact, this is difficult for people who are too big to enter the shaft smoothly. Yes, I'm talking about me at that time. How many rubs they can get per day? The zircon rough that miners get every day is very unstable. Usually, a small can a day is a good gain. You can see the original color and how small the pieces are. Therefore, when the miners find the zircon rough, they will sell them to the first collector, and the first collector will sell them to the second collector. In this chain, they only sell original rough which has not been heated. So, let's start, negotiate, and gambling. Cambodian zircon rough is different from other rough. In addition to evaluation of the rough itself, there is a big risk. That is color. Usually, I will follow 4 criteria when I select rough. Color. In addition to the stone's body color, there is another great issue about whether the color of Cambodia zircon can turn into the blue we want after heating. These 2 issues let the evaluation have great risk. Shape. Rough shape decides the final weight of the gemstone. In the past, there was no effective technical improvement for commercial cutting factory, and they often gave up the beauty of gemstone in order to reduce loss. Now, we can control the gem weight and fire through scientific evaluation to our accurate faceting skill. Crack. The crack of rough is a very important judgment condition. An embarrassing crack will not only be troublesome to the faceter, but sometimes greatly affect the value. Inclusion. Not all inclusions are bad, and we are not just looking for completely clean rough. How to make a decision of inclusion is a very important subject to test faceter when buying rough. When I first went there to select rough, I also tried to find a master to heat rough and make detailed records of the sample. After knowing the local heating methods, I took most of zircon rough without heating and back to Taiwan for more scientific, stable, and more successful heating. Now, let's see how to heat zircon rough there and the result. Let's see how local people heat rough to change color. First, we need to prepare 2 crucibles, one large and one small. The new crucible needs to be heated and dry first. Otherwise, it cannot be used immediately. After drying the crucible, add in zircon rough and seal it with soil. Heater will heat the tank to more than 1000 Celsius degree with charcoal and blower. At the same time, put the crucible next to the fire and heat it up together. After the temperature reaches the target, clamp the crucible into the flame. About 10 to 20 minutes. Take out the crucible, wait for natural cooling, and then open them layer by layer. Time to open the first layer of crucible. Although it has been cooling naturally, the temperature is still high. We can see that the soil of the outer crucible has crystallized at a high temperature. The master is now hit the crystal layer of the outer crucible with an axe to take out the second one. Let's come to the second layer. We can see that the soil sealing the second layer of crucible does not have strong crystallization as the first layer due to the different temperature and environment. The picture is very beautiful, but I just want to hurry up the result of this gambling, so I don't have the chance to enjoy it at that time. After open the second layer of crucible and pull out the rough, you can see the change of color. At this time, the stone is still in high temperature. We can see that not all rough are changed into the same blue. Some blue is very charming. Some have changed from reddish brown to light green or colorless. And many rough surfaces are scorched. In fact, changing the color of the rough itself is a gamble. The other risk is using traditional unscientific heating method will let many rough with good color are burned by high temperature during heating. So, how do you think about the result? Win or lose? Next, I will take you to see the local preform process of zircon after heating and explain why preform is needed in gem cutting, especially in commercial cutting. After the preform, we will enter the process of cutting and polishing. You can see how gemstones are fixed to tool arms, cut and polished, and also see the tools and methods used by local cutters. These methods have strong regional characteristic experience of local factories. Because the cutting method is quite traditional, there is a big technical gap with the precision faceting we use now. So, when I go to Radiometric again, I bring some simple measure tools and share my knowledge to help the factory to improve their cutting and quality. Next, let's compare the results of using traditional heating and commercial cutting in Radiometric with scientific heating and precision faceting in Taiwan. After the introduction of zircon from Cambodia, I will take this rare opportunity to present my series of works. You can see the difference in technical level, hand-down value, and artistic between precision faceting and commercial cutting, which certainly accounts for the vast majority of gemstone in the gem market. Finally, I would also like to introduce to you my precision faceting course and faceting machine, Dreamer. I hope to make more people fall in love with this beautiful career and enjoy together. Why they need to perform? First of all, because the color of zircon rough heated into blue is directional, which means that the blue color can be fully displayed only when the stone is fixed at the right angle. Therefore, local workers will first look for the angle position with the strongest blue on the rough. Fix the rough on the metal rod with red wax, and then fix with experience to set it most suitable shape for cutting. Another reason is that after the preform, the local heater will heat the preform stone again. They believe this action can get better blue color of the stone. Although such method is not quite scientific, they will put the bed rough surround the preform stone and put it in the crucible during the second heating to avoid high temperature damaging the preform stone. In this step, they can have the opportunity to provide the stone with complete color transfer again in a friendly environment. This is a common tool for grinding stone in Cambodia. It is small and simple, easy to install and does not need to be plugged in. It combines the grinding wheel of diamond powder, fixed support, and rotating handle. Locally, it is usually used to grind the outer shape of stone. The worker will fix the tool on the table and put a container containing water and sponge under the grinding wheel to ensure that when the wheel rotates, the sponge can give water to the wheel, and let the ground powder of the stone into the water. Bricks will be placed next to the wheel to provide a suitable height for grinding. Let's see how to preform stone in this tool. The worker will turn the handle with one hand to drive the wheel to rotate. At the same time, the other hand holds the doping stone and grinds it with the side of the wheel. You can see that there is no need for electricity and other major tools during and after work. The appearance of the stone is ground completely by eyes and experience of workers. In this way, the gem sellers who do not have scientific knowledge of commercial gemstones often boast that this way can save much more weight of stones. But is this really the case? I don't think so. After preform and reheating, we go to the next process. Stick the stone on the metal rod, cut and polish it. How they cut and polish stones? First, hit a new piece of red wax with a candle. And stick it to the metal rod. Next, The target stone is heated to a temperature at which it can stick to the wax. After that, press the stone into the red wax. Continue to bake the wax with fire to make it in a semi-milling state. At the same time, adjust the girdle line of the stone or the table of the crown to maintain to a 90-degree angle perpendicular to the metal rod. Check it with ice and press the wax a little bit to cover and surround the whole stone. Similarly, these movements are carried out by hand, eye feeling, and experience without using measuring tools. This process is called doping. After doping, workers will clamp the metal rod on the working arm and adjust the angle between the arm and the metal rod according to their eyes and experience. The working arm will be placed on the glass, which is aligned and parallel to the lab surface. The working arm touches a metal bar erected on the table to ensure that the arm can go out of a straight path when grinding and polish on the surface of the lab. During the polish process, the stone will be soaked with water continuously to avoid the instantaneous temperature of overheating during the polish of the stone in the high-speed operation of the lab. This is another local factory, which is also doing the polishing process. You can see that they move very fast every time, making the coordinated action of eyes and hands in the whole process. Moreover, because the speed of the lab and the hardness of the surface are the huge pressure on the stone, this method will create a flat surface on the stone with violence. The method is also applied to the traditional diamond polishing. The biggest difference from diamond polishing is that the polishing action of high temperature gasification on the diamond surface through the correct direction and huge pressure. While collagen stone use similar equipment, they use huge pressure to forcibly remove and press the stone surface. The application mode is very similar, but the action principle is different. Unfortunately, such observation without loop and the adjustment of polishing angle by feeling are distinct only to win rapid process time. But the quality of the stone itself is still quite rough. In addition, the physical and optical properties of zircon have not been correctly expressed, and the vast majority of zircon in the gem market cannot really show its optical beauty, reduced to a low evaluation that only looks at color and weight. So, I try to provide some suitable ways to help them improve the quality of this process. Because too complex tools cannot be used locally, I choose simple tools that can be clear to help them. The first is the angle ruler, which can easily measure the angle of the metal rod on the working arm. Each different gem has its own unique physical and optical properties. For example, the refractive index, just like light entered in water from air, will deflect at an angle. The same will happen inside the gem. When the light enters in the gem, can it return to our eyes again according to the light path we designed? This is whether the gem has good total internal reflection and whether the gem will have a window. Because different kinds of gemstones have different refractive index, there is a special angle on the refractive index, which is called the critical angle. When the stone meets the requirement of the critical angle, the total internal reflection can be complete to the greatest result. Therefore, through the angle ruler to ask workers not to be lower than the angle requirement, will be able to judge the optical quality of gemstones more scientifically. And optical quality is the real essential pursuit of our faceting division. Instead of explaining complex knowledge, I first use drawings to let the factory owner understanding the meaning of this tool and how to use it. Then, the factory workers were told how to measure the angle on the working arms with the angle ruler, in which angle can meet the optical condition of gemstone. In this way, in addition to allowing some rough with smaller cutting size base to leave more weight, it can also avoid cutting the stone pavilion very thick in order to pursue the optical effect. Another tool is tenfold loop, which can help them improve the quality after cutting and polishing, so that they can see what positions needs to be adjusted, not just with their eyes. The above is my introduction from the mine to the final processing into zircon cut stone in Cambodia. Next, we will simply compare the processing quality from heating stone to grinding and polishing. At the same time, it can also let you know how different this will be. Before comparing heating methods, I need to make a special statement that knowledge and science have always been the path we pursued. There are still too many questions in this world that have not been completely solved. Taking Cambodia zircon as an example, this way of changing the rough from reddish brown to blue color through heating, that we only know this method can be achieved color change. But in fact, until today, we still do not have a clear conclusion to prove mechanism of color change and how to scientifically control the changes. Even we can confirm the color or inclusion of rough before heating fruits, tools, or methods to turn into the top blue color after heating. This heating analysis is based on the data obtained from my actual heating record in local area. Due to the heating of stones through charcoal and blower, It is difficult to accurately control the temperature and the speed of temperature rise and fall. Therefore, there will be a very high percentage of them because too high temperature heating will cause burning loss. In the picture, the red circle is the top blue rough after heating. The blue circle means that the rough is only light blue. The green circle means that the roof becomes light green after heating. And the white circle becomes completely colorless. Finally, the yellow circle is the burnt rough. If we convert this result into percentage, we will find that 57% of the total rough can be used, while 43% of the rough is colorless and burned. This means that if the zircon is heated locally and there is no better protection technical support, there will be a large percentage of unnecessary loss. If someone wants to purchase and heat rough here, we do not consider the color and state of the rough itself. Nearly 50% of the rough will be consumed due to the temperature in the whole batch of heating. Unfortunately, in the local, we can only buy and heat rough, and the seller will not be willing to sell the heated blue rough because this is a big gamble. Next, I brought the heating rough back to Taiwan and heat it in a scientific way. I divide this rough into several parts and made record on the details of temperature control. Finally, the whole batch of rough is classified in color and size. The red circle is the top blue and large size heating rough. The white circle is the medium size top blue rough. The light blue circle is the light blue rough. The green circle is the light green rough. And the last yellow circle is a rough that has been heated without changing color. Among these rough, there is no rough burned and consumed due to too high temperature, which proves that as long as careful and accurate temperature control is carried out, unnecessary consumption in the heating process can be greatly reduced. Of course, these rough are selected based on my knowledge of faceting. They have carefully selected their color and inclusion characteristics from the original whole batch of unheated rough. It can be proved that such selection still cannot be completely heated and it will be the top blue rough. Can only improve the relative probability. These records will also become an important reference for me to select a heat rough in the future. The next step is to compare of polished stone in these two places by iPhone camera. Due to the local requirements for workers in Cambodia, the stone pavilion, that is the lower half of the gym, is usually made particularly thick in the preform stage. To prevent the gym half window, We can say that more than 80% of the gemstones in the gem market have serious window problems. But because in the whole process of grinding and polishing, every surface made on the gem is only rough. So when the light enters the gem and returns to our eyes, it will truly reflect this situation. You can see that the light spot inside the gem is in a disordered state, which can only show that this is a gem with reflective brightness at most. This stone is a work of precision faceting with the rough heating by myself. It can be seen that light through the flat surface of the stone can not only make the stone look shining, but also master the changes of light when reflected. To structure a richer expression of light inside the stone, you can also clearly see the strong birefringence inside the stone in the photo. Human eyes are very sensitive to color and visual balance. There is no harm without compression. Therefore, when the two gemstones are put together, we can clearly distinguish its symmetry in appearance and whether the light has the correct reflection. In addition, due to the different quality requirement of the stone surface polishing, it can be seen that the two stones express a clear visual state, which is also completely different. The expression and symmetry of these light levels are the real value of the gem faceting. For me, gemstones are the most precision gift of nature, and the process from the rough to gemstone gives more human aesthetic and light expression. Pursuit of beauty of each rough is the mission and romance of precision facetors. Next, I will take a rare opportunity to introduce my series of works of last year to you, in search for numerary. Art is a kind of real expression, but the human eyes will see the light evenly. Therefore, we record and convey the real brilliance of gemstone through photography. Let photography become an irreplaceable art. In this introduction, gemstones published without modification through photography present the most real world under the lens. Under the sky, everything is endless. Animals, plants, and minerals combine to form a rich nature. We as gemstone facetors pick out the beams to penetrate the gem, pay tribute to nature with words. For hundreds of millions of years, minerals have evolved with geology, creating local elements, precipitation, and crystallization, forming intense crystals in the geological system. They are treasures of natural history and have become chapters of human history. Faceting the perfect gemstone requires considerable meticulous development and sophisticated equipment. In order to perfectly guide the facet of the light, I cooperate with my partner to design and own my own faceting machine, Dreamer, to achieve the perfection of dream faceting. The original rough is buried underground or in the river. When it is excavated, after cutting and polishing, the artist gives the gem another important element of nature, which blooms in intoxicating splendor. This important element is light. Because the world has light, it also has darkness and color. As the light that illuminates gems and displays their colors, it is a particle, a wave, physics, and mathematics, and it can exist in two-dimensional, three-dimensional, and even higher dimensions. I pick up the skylight and redesign the direction for it, using light as the so-called of the gemstone, introducing into the gemstone, creating an internal space of light, shadow, and color, as well as the construction of the depth of the light and shadow. The brilliance and energy of the light are explored into the environment outside the gemstone from the inside out. The artist used this light to pay tribute to nature. Out of the experience of nature and the construction of the spiritual world, the artist has also redirected the expression of materials and the imagination of people. Like architectural design, architects from different styles and concepts through the design of external forms and internal structures. Today's dream appreciation is still at the stage of appearance, color, and brilliance. I hope to make bolder use of precision faceting and contemporary technology to move the design life path and turn the gem from appearance of a well-designed building into a glass house. The roof of the glass house is like a dome of a gem, allowing light to shine through it. Those inside gemstone constantly reflect the intertwined light and shadow, and the rich color separates by dispersion, shape the space with light, and construct a different appearance of an extraordinary world. Although it is made by humans, it is like heaven. I am fortunate to be born in this era. The gems given by nature and the skyline of the rainbow allow me to incorporate gemology, mineralogy, mathematics, optics, photography, and contemporary technology, ideas, and perceptions, so that the character and form of gems can be seen from material terms and get into the spiritual aspect of physical layer. In the future, we will continue to pick out light and introduce new art forms of gem faceting. Design blueprints with light, shadow, and color, and gemstones' eternal beauty to trap within a time capsule. Thank you for joining with me. Wow, this is the last part of my speech. I will quickly introduce my baby, precision faceting machine, Dreamer. If you want to know more about Dreamer, please visit our website, dreamerfaceting.com. Because Dreamer's design is specially developed for my operation. It is also suitable for my precision faceting teaching system and faceting standards I create. In order to ensure that those who use Dreamer can correctly maintain and fully enjoy it, only my students can buy it now. In addition to Dreamer, I also developed faceting lab more suitable for precision faceting. It's called DreamLab. DreamLab is suitable for facetors who want to continue to improve the quality of faceting. In addition, I specially developed the faceting education system. Students have verified its success of machine and education system through competitions. It is expected that the international course will restart in June this year. If you are interested in learning and entering this beautiful world, please contact me. Thank you.
Well, I have to apologize for the evolution of sound quality at the end there, and Daniel has weak video and connections at his end. So, at any rate, we've come to the conclusion of our program today, and I want to thank all of you that stayed with us because there was some very technical things going on, and it was a very different kind of program today. Thank you, George, Daniel, and very much thanks to Robin as well, and to you as attendees. Now, I'd like to throw out there, as I do at the end of each program, a bone, and this is a request for leads to be a speaker and presenter on our next program in May, which would be on turquoise. So I'm looking for experts on turquoise to share with us. A very interesting stone, I think, one that's has moved into prominence in the United States, where it used to be only found and considered to be the best in the world was from Persia. We now have very, very good turquoise coming from a number of sources. So I want to challenge all of you to put your thinking caps and your connection caps on and get back to me with some leads for turquoise. And after that, in June, we're looking at pearl. I know it's the first non-mineral gem that we'll be talking about, but it's an extremely important gem in the world of jewelry and gems. So I think we should be looking at pearls as part of the program that we are doing. And I know there are people out there that have expertise in that area. For those who got up early in the Orient, like Daniel and Ida and Miro, thank you for joining us and supporting Daniel and us. And I look forward to you joining us when you can in the future, even if we don't have your Daniel as our presenter. So hope you have a great day, what's left of it. Thank you all for participating. Thank you for your questions. Antoinette, appreciate that. You always come up with a few. And look forward to your joining us again next month at the last Sunday in May. And you can unmute.
I'll be there. This was great. I loved it.
And thank you, Ray, for organizing all of this.
Absolutely.
Yeah.
And I think each of the speakers who gave really interesting presentations that touched on various tangents that are so infrequently discussed in my world, the gem world, but really relevant and really important. So I really think we need to get more people involved, hearing from people like each of you who are here today, and the other one I attended as well. They were great.
And they're just getting better and better. So fantastic work, everybody.
Yes, really.
All right. So ciao for now, guys.
Yeah,
Thanks for
ciao.
coming.
Ciao for now is
Thank
right.
you.
Do you
Thank
want to
you.
announce the date of the next one, Ray?
The date of the next one?
The
Yes.
last Sunday in May.
May.
Last
Got it.
Sunday in May. That's easy. Okay.
Last Sunday. Got it. I'm
We're
putting it on the
always-
calendar now.
We're
Okay.
always the last Sunday of the month.
Mhm.
And we try, and with the exceptional changes due to, daylight savings, which has messed us up in some instances, we're sort of coming to grips over that. So looking forward to you all. Thank you for attending. And I hope that you all got something good out of this.
Yes.
Thank you all.
Thanks. So long.
Bye.
Bye-bye.
Bye.